Hello Algebra 1 students, this is Mr. Wilsey, and for this video you're going to need to take down some notes on grid paper. I want you to title your notes, Algebra 1, Systems of Linear Inequalities. Alright, now in this section we are going to encounter problems that ask us to do this, for example. Example number 1. Graph the linear inequality y is greater than or equal to negative 3x minus 2. So the first thing we're going to need is a set of axes. Preferably use a straight edge to grab to plot your axes. There we go. This is x, this is y. Alright, so y is greater than or equal to negative 3x minus 2. Now, the place to start when graphing a linear inequality now is to graph this as if it were an equation. So you know how to graph y equals negative 3x minus 2. I'll put that in a thought bubble. The way to graph that is go down 2, that is your y-intercept, and then the slope is negative 3. So you're going to rise negative 3, run 1. You can go backwards as well. Okay, so we have some points here, and in this case we have a greater than or equal to sign. That means that we're going to put a solid line, just like you're used to doing. You use a solid line whenever you have a greater than or equal to sign. Now, there's one more piece that we have to add to this graph because we're dealing with a linear inequality in this case. Because that's a greater than sign, we are going to have to shade. So I forgot to mention this, but you're going to need to have two different colors of pens or colored pencils in order to watch this video and in order to take notes appropriately. So because that's a greater than sign, we're going to have to shade above the line that we drew. The best way to shade is maybe something like this. Okay? So you don't have to go too crazy in your shading. You don't have to make it completely dark. But this is sufficient for our purposes. Now, let's talk about what this linear inequality actually means from the graph. The way that we've shaded this means that I can pick any ordered pair up in the shaded area, or in this case, along the line itself, and that ordered pair will make that statement true if you plug the x and the y into their places. So for example, this point right here. The ordered pair of that point is 3, 2. X is 3, y is 2. Now if we put those numbers into the inequality up here, so we'll put in 2 for y, and then negative 3 times 3, and then the minus 2. So I just put the ordered pair into the inequality, and I got that. Now, I'm going to simplify a little bit. Negative 3 times 3 is negative 9. Negative 9 minus 2 is negative 11. Now, notice what we found here. 2 is greater than or equal to negative 11. And this is a true statement. Now, I could have picked any ordered pair in here. And if I plugged it in, I would have gotten a true statement. So that is what this graph actually represents. It tells you what x and y values, when you pair them together and stick them in here, will make a true statement. Now in this particular case, if I took a point on the so-called boundary line, for example, if I took negative 1, 1, negative 1 comma 1 is on the boundary line. Let's put those into the inequality and see if we get a true statement. So 1 goes in for y. 1. Is that greater than or equal to negative 3 times negative 1 minus 2? Let's see. We're going to simplify. Negative 3 times negative 1 is positive 3. 3 minus 2 is 1. So is this a true statement? Is 1 greater than or equal to 1? Well, yes, it is equal to. Okay? So that is also a true statement. All right, let's graph one more inequality. So example number 2. Graph the linear inequality y is less than negative 3 over 4 times x plus 1. All right. So we're going to start by putting our coordinate axes down. Labeling them. Oh, I forgot my scale in the last problem, but we can automatically assume that the scale is 1 in the x and the y direction. All right, so we're going to plot the y-intercept, positive 1. The slope is negative 3 over 4, so I'm going to rise negative 3, or run positive 4. Then I'm going to go backwards, 4, 3, going to be right here. All right, now before I plot the line, notice the sign. It is a less than sign. There is no bar beneath the less than sign, just like there was a bar here. That means that instead of a solid line, like I drew up here, I'm going to draw a dashed line connecting these points. So, perfect. Okay? So I want to be clear about that. If there is no bar beneath the sign, you draw a dashed line. If there is a bar, you draw a solid line. Now, we're not quite done graphing this inequality. The last step is to shade. I can either shade above the line or below the line. The way that I tell is by looking at the sign. Y is less than negative 3 over 4x plus 1. Because it's a less than sign, I'm going to shade below the line. So all of the y values that are below that line will work. There we go. And we are done. All right, now let's take a look at a slightly different type of problem that you're going to be experiencing. Example number 3. All right. Graph the system of linear inequalities. That would be the directions. Y is greater than or equal to 3 over 2 times x minus 2. And then the second inequality is y is less than 1 over 4 times x plus 3. So in this case, we are dealing with a system of linear inequalities, which means we have 2 inequalities here. So let's graph these exactly the same way that we did with the previous problem. I just realized that this grid paper on the back side is much smaller, much finer than on the other sheet of paper I was working with. All right, so the first inequality. Now, this is where we're going to need to use different colors. Okay, so I've got red and blue here. Make sure that you have 2 different colors of pens or pencils or something. Okay, so I'm going to graph the first one in red. Negative 2 is the y-intercept, so I'm going to plot a point there. The slope is 3 over 2, so rise 3, run 2, rise 3, run 2. Let me go backwards a couple times. Okay, now this is a greater than or equal to sign. Because of that bar, I know that I'm going to draw a solid line. Perfect. Now, change colors. let's graph this inequality on the same grid in blue. So y-intercept is positive 3. The slope is 1 over 4, so rise 1, run 4. Rise 1, run 4. We can go backwards. Now in this case we have a less than sign. So that means that I'm going to draw a dashed boundary line. I can't speak today. Remember that the line that we draw is called a boundary line. That's important. Perfect. Okay, so I forgot to do this with the red one, but let's do the blue one here. That is a less than sign, so that means that I'm going to shade below the blue line, and I'm going to shade in blue. Okay, so I'm shading everything below the blue line in blue. Now let's go back to the red line. That is a greater than or equal to sign, which means I'm going to shade above the red line. Perfect. Now, this is getting rather complicated, as you can tell. And in fact, it's not entirely necessary to do all of this shading when you're graphing a system of linear inequalities, because the most important thing that you want to shade is the overlap. Okay? Shade the overlap. So wherever I see red shading and blue shading, I'm going to shade that extra dark, and I'm going to shade it in black. Okay? So the overlap is going to be, actually that's not black, this is black. Right over here. And then I'm going to stop at this point here, but I'm going to stay above the red line. So I'm staying above the red line and below the blue line. I'm going to shade that in extra dark. Perfect. Now, as you can tell, graphing systems of linear inequalities gets very messy in a hurry. Alright, let's extend this problem a little bit further. What if I asked, is the ordered pair -4, 1 a solution to the system, oh my goodness, I can't spell, to the system of linear inequalities? Now, what you have been doing so far is graphing and solving systems of equations. The solution to a system of equations is the intersection point. But when we're dealing with linear inequalities, the whole shaded area is the solution. Any ordered pair in the shaded area where the red and the blue overlap is a solution. So when we are asked a question like this, is a certain ordered pair a solution to the system of inequalities? All we have to do is graph the system, highlight the overlap, and then identify whether or not that ordered pair is in the overlap. So let's try to find where -4, 1 is. I know it's kind of messy, but let's see here. The origin is right here, so we're going to go 1, 2, 3, 4 to the left, and then up 1, right there. Oh my goodness, that is awfully hard to see. So -4, 1 is, in fact, in the overlap region. That means that, yes, it is a solution to the system. Now let's check that in a different way. Let's actually plug -4, 1 into both of these inequalities and see if we get true statements for both of them. So let's plug it into the first one. So the first inequality was y is greater than or equal to 3 over 2 times x minus 2. So let's plug in 1 for y. and then let's plug in -4 for x. Let's simplify. 1 is greater than or equal to 3 over 2 times -4 is -6 minus 2. So 1 greater than or equal to -6 minus 2 is -8. So is this a true statement? Is 1 greater than or equal to -8? It certainly is. So that checks out. But what we're going to have to do next is plug -4, 1 into the blue inequality. Let's put in 1 for y. 1 is less than. Actually, there should be question marks up here. There should be a question mark up here because we're not quite sure. That's what we're doing. We're checking to see whether or not the statement is true. 1 less than 1 over 4 times x, which is -4, plus 3. So is it true that 1 is less than 1 over 4 times -4 is -1 plus 3? Is it true that 1 is less than +2? It is indeed. So this checks out. So the ordered pair makes both of these statements true, so it is indeed a solution to the system. But this is a lot more work than you need to do. To me, it's easier to graph it and see visually that yes, the ordered pair is in the overlap region. Alright, now let's try a slightly different type of problem here. Now, in this case, we are given two different graphs. So let's just look at one graph at a time. I'm going to hide that one for now. So the graph on the left here represents a system of linear inequalities. And our goal is to write the system of inequalities. So let's look at the blue line first. So first thing we want to identify is the y-intercept. It is +3. So +3. Now what's the slope? What is the slope? Let's see, we go down 3, and then we go over 2, and it looks like we're back on the line. So down 3 over 2 means the slope is -3 over 2. And that's going to multiply the x. And then we're going to have a y on the other side of the inequality. But the question is, what sign goes here? It's not an equal sign, which is what you're used to dealing with. It's going to be either greater than, less than, greater than or equal to, or less than or equal to. Now, the way to tell as to whether or not it belongs here or it belongs here is look at whether or not the line is dashed. So in this case, the blue line is dashed, so we know that it's either a greater than or a less than. Now, look at the way it's shaded. It might be kind of hard to see in the video, but it is shaded below the blue. It is shaded below the blue. So that means it's going to be a less than sign. So y is less than -3 over 2x plus 3. Now notice something else here. Even though the line technically stops right here, actually no, it doesn't technically stop right here. Just because in the graph it stops there, the line actually keeps on going on and on forever. So that's why we're shading over here as well, because if we were to extend the line out, it would still be below the line. Alright, now let's write the equation for the red graph, the red line. So, this is kind of challenging now. We have a vertical line. Do you remember how to write a vertical line? Write the equation for a vertical line? In this case, that vertical line is going to be x. X is going to be over here. There's not going to be any y. Now, from the origin, we go over to the right before we hit the line. We go over to the right 1. So that means it's going to be x and 1. Now, ordinarily, the equation of that line would be x equals 1. Okay? But in this case, we're writing an inequality. And we are shading to the left, which means all of the x values over to the left of that line are going to have x is less than 1. Notice again that because it's a dashed line, I use just a less than sign as opposed to a less than or equal to sign. Now we have one more question we want to ask. Is -1, 2 a solution to the system? To answer that question, all we have to do is look at the graph. First of all, we find where -1, 2 is. We go here, -1 up 2. So -1, 2 is right here. -1, 2. Now that point is below the blue line, and it's to the left of the red line, which means it's in the overlapped region, which means it is a solution to this inequality, to this system of linear inequalities, which means that, yes, -1, 2 is a solution. All right, fantastic. Now, let's take a look at this graph. Again, the first step, let us write the equation of the red line. So there's going to be a y, and there's going to be an x. The slope is rise 1, run 1. So the slope is 1, and you don't have to write the 1 in front of the x. The y-intercept is +1, so x plus 1. Now the question is, do I use greater than sign, less than sign, greater than or equal to, or less than? Less than or equal to. Well, the line is dashed, so we know it's going to be either less than sign or greater than sign. And we are shading above the line, which means y is greater than x plus 1. Now, let's do the blue line. Let's write an inequality for the blue line. Now, in this case, we have a horizontal line. A horizontal line has a slope of 0, so 0 times x will make the x disappear, which means we're only going to have a y, and there is no x, we're just going to have a number on the other side of the inequality sign. In this case, the number is the y-intercept, which is 2. So y and 2. Now, it's a solid line, which means we're going to have one of these two symbols, and we are shading above the line, so y is greater than or equal to +2. Fantastic. Now we've done our job. We have written the system of inequalities. Now let's answer this question again. Is -1, 2 a solution to the system? Well, let's see. -1 up 2 right here. Uh-oh. That's interesting. -1, 2 is right on the boundary line. Now, -1, 2 is certainly above the red line, so -1, 2 will work for the red inequality, but does -1, 2 work for the blue inequality as well? Well, yes it will, because this solid line indicates that any ordered pairs on the line will make that inequality a true statement. And you can just check that if you want. See, the y value is 2, so 2 is 2 greater than or equal to 2? Well, yeah, it is. It's equal to 2. So that checks out. The x value doesn't even come into play there, because there is no x. Now, if we were asked a question like, let's say, is 2, 3 a solution? Over 2, up 3? Is that a solution to the system? In this case, even though it's still on a boundary line, this boundary line is different. This boundary line is dashed, which means ordered pairs on that boundary line cannot possibly be solutions to the system of inequalities. So 2, 3 is not a solution because it's on a dashed boundary line. Alright, that is it for this topic. I hope you learned something and that you took good notes.